This is the second lecture for Module 2 of Unit 2, which deals with miscibility-ideal and ideally dilute solutions. This second lecture concerns ideally dilute solutions and Henry's law. Henry's law is, as you will see, a law that describes extremely dilute solutions, which is most often applied to solutions of gases and liquids. Gas molecules have more energy than liquid molecules as a rule. They're moving much more rapidly. And gases do not dissolve readily into solution. You will see some dissolution of gases into a liquid at relatively low pressures. The concentration of gas in the liquid can be increased by increasing the pressure of the gas above the liquid. As the concentration above the gas above the liquid increases, more gas enters the liquid phase. Again, you will see a balance that exists between pressure of the gas above the liquid and concentration of the gas in the liquid. An equilibrium between gas molecules escaping from the liquid and dissolving into the liquid. And again, to summarize, by increasing pressure, more gas can be forced into the liquid, increasing its concentration. This, by the way, is another example of Le Chatelier's principle. Henry's law says that the concentration is equal to the pressure multiplied by some constant. So as we've seen, if pressure goes up, concentration must also be going up. Or, since concentration of gas at a certain pressure is equal to this constant, we can say that concentration over pressure at one pressure is equal to the concentration over the pressure in another set of conditions, where C1P1 equals C2P2. This process form of Henry's law allows us to describe what happens to the concentration of a gas in a liquid as the pressure of the gas over the liquid goes up or down. Here are some example Henry's law constants for various gases. Note that the units, in this case, it's reciprocal, it's moles over liters times atmospheres. The pressure you would use with this form of Henry's law would be atmospheres. And concentration units with this form of the Henry's law constant would be equal to moles per liter. Again, gases are not very soluble in water, so you will see that all these constants are multiplied by 10 to the negative 4. Note the Henry's law here is in a numerical example. The Henry's law constant for oxygen and water at 25 Celsius is 1.27 times 10 to the negative 3 molar per atmosphere, or mole per liter divided by atmosphere. And the mole fraction of oxygen in the atmosphere is 0.21. Calculate the solubility in grams of water and oxygen at 25 Celsius, considering a typical atmospheric pressure of 1 atmosphere. Right, you should attempt this before continuing in this presentation. But first, as a hint, or to get things going, according to Dalton's law, the partial pressure of oxygen is proportional to the mole fraction of oxygen. We know that from Gen Chem I. Or, partial pressure of oxygen in this case is 0.21 times 1 atmosphere, or 0.21 atmospheres. Alright, if we know the Henry's law constant and the partial pressure in atmospheres, it's straightforward to solve for an oxygen concentration of 2.7 times 10 to the negative 4 molar. And then if we want to know grams per liter, we multiply moles per liter by grams per mole to obtain an oxygen concentration in grams per liter. This quantity is important for supporting aquatic life like fish, which breathe, oxygen dissolved into water. Here is another example involving the solubility of carbon dioxide of water at 0 C at a pressure of 3 atmospheres. The solubility of carbon dioxide is 0.348 grams per 100 milliliters at 0 C in 1 atmosphere. Okay, note that you cannot use the Henry's law constant for carbon dioxide that appeared earlier in this lecture on a table, as that one applies at 25 Celsius. However, you have enough information here in this statement to solve the problem. The solution is, this is a straightforward process form Henry's law problem. We relate C2 over P2 to C1 over P1 and solve for the concentration under the second set of conditions, which is to say the concentration corresponding to 3 atmospheres. First set of conditions, C1 and P1, are 0.348 grams per 100 milliliter in 1 atmosphere. Algebraically, C2 is C1 times P2 over P1, which gives a concentration of 1.044 grams per 100 milliliter. Again, we see that concentration of the gas increases as pressure increases.